Inverters. What is an inverter? An inverter is a device that converts DC supply into AC supply at the desired output voltage and frequency levels. Inverter term is not new to us. We have already discussed one kind of inverters, that is the line commutated inverters, during the phase control converters. Let me go back to the phase control converters. A phase control converter is capable to work as a rectifier or as an inverter. If in a converter the value of alpha is kept between 0 and 90 degree, it works as a rectifier. However, it is said to be working like a line commutated inverter if the value of alpha is between 90 to 180 degree. But that line commutated converter has some limitations. What are those limitations? A line commutated inverter cannot function as isolated AC voltage source, or it cannot give you the variable frequency at the output side. It is this term line commutated inverter, it is used in relation to the phase control converters when the load is RLE. So for the machine load, when it is under the regenerative mode, let us say for traction purpose, if the machine is under the regenerative mode, then for quite some time the converter behaves like a line commutated inverter. But here in this chapter, if I say inverter, I will not talk about the line commutated inverters. I will be discussing about the force commutated inverters. The inverters which can provide you the AC output voltage which is adjustable, an inverter which provides you the voltage at adjustable frequency. That inverter I shall be discussing in this lecture. So this lecture will cover the discussion on force commutated inverters, and these are the inverters which are widely used in industry, in public sector, for the power sector, for our homes, domestic, industrial, commercial, everywhere you will find the application, the use of an inverter. Let us see what are its applications. The inverters can be used for adjustable, this is the major use, adjustable speed AC drives. This is the major use of an inverter. It could be used for static VR compensation, for voltage compensation, facts. For HVDC also inverter is required, for UPS and for active filters. These are few of the applications which uses inverter. Among these applications, as I said, adjustable speed drives. This is the application which is the most common. Now, how these adjustable speed AC drives works? In this is called, in short, we can call it ASD. In ASDs, the supply is an AC supply. This supply is fed to a rectifier which converts this AC into DC. This DC supply is then again converted into AC. So basically gives you a two-step conversion where a rectifier and an inverter is used. So in ASDs, this inverter forms a part. This is called DC link. So inverter is connected between the load and the DC link. In HVDC as well, the AC is first converted into DC, then DC is again converted into AC. There also, in HVDC also, we use an inverter. So wherever DC is to be converted into AC, we use an inverter. And generally in ASDs, like the example that I've considered here, in ASDs we require a variable voltage and a variable frequency at the load. To vary the voltage and the frequency, we can play with the firing angle of the devices connected in this inverter. Now, how that control is achieved, how the devices are fired to get the conversion from DC to AC, this we shall be discussing in this lecture. There can be various types of inverters, VSCs and CSCs, voltage source converters and current source converters. Here, since I'm talking about inverter, I'll call it a VSI and a CSI. This voltage source inverter is the most common inverter because generally it is also called voltage source or voltage fed inverters, VSI or VFI. So if the inverter is fed by a stiff voltage source, it becomes a voltage source inverter. And if it is supplied by a constant current source, by a stiff current source, then it makes a current source inverters. In general, most of the times the supply is through a voltage source. So this first type of inverter is the most common one. Inverters can also be classified based on the connection of devices. If the devices are connected in different fashion, they configure different inverters. There can be three types: bridge inverter, series inverter, and parallel inverter. Based on conversion, if an inverter is converting DC supply into single phase AC, it becomes a single phase inverter. In single phase inverter, we can have half bridge inverter or a full bridge inverter. If a If an inverter is converting DC supply into three phase, then it becomes three phase inverter. In three phase inverters, there are two modes in which it can work. One is 180-degree mode and another is 120-degree mode. In all my further discussions, I shall restrict myself to, from this side, I shall be discussing more on VSIs, more on bridge inverters. I shall discuss both single phase as well as three phase. In single phase, I'll discuss these two. In three phase, I'll discuss these two. I shall touch upon the intro of current source inverters. What are these inverters? How does it work? I shall discuss about the series inverters as well, how these inverters work. So in this complete chapter, I shall be, except parallel inverter, I shall be discussing about all the inverters. So let us start the discussion with single phase bridge inverters. Now what is a bridge inverter? It is basically a VSI. As I said, most of the inverters are VSIs because the supply in general is a voltage source. So this bridge inverter, it could be a half bridge, it could be a full bridge. So based on the number of devices connected and the supply, we can classify the bridge inverters as half bridge and full bridge. This configuration uses two transistors and these two diodes. I shall later on discuss the purpose of using these diodes. These two controlled devices are used in half bridge inverters. In place of these transistors, you can also use the thyristors. In fact, you can use any control device. In general, for low and medium power applications, the inverters, in place of these thyristors, the inverters generally use GTOs and IGBTs. If it is a low and medium power application, you will find that in place of these devices, you are using an IGBT. For low, like the inverters that we are using in our homes, because those inverters are rated at 1 kVA or 2 kVA maximum, maximum up to 5 kVA, those are using MOSFETs. But for medium power applications where we talk about the VFDs, the variable frequency drives, the AC drives, which are used in industry, all those drives are based on IGBTs because their rating is up to several hundred megawatt, several hundred kilowatts. So those devices, those inverter are made using IGBTs, and for the very high power levels, like in case of HVDC, we use the thyristors as these devices. Now, half bridge configuration is not much used, but yes, for the understanding, we shall discuss the half bridge inverter as well. Now, this half bridge inverter, which I have considered here for the understanding, it uses two thyristors T1 and T2. At the supply side, you will find two batteries are connected. Now, we wish to get an AC supply at the load. If we fire this thyristor T1 at this instant, then we shall receive this supply. This battery will be connected to load and the current will flow in this direction. If I consider this side as positive, this side as negative, and call this voltage as positive, then I can draw here the output voltage as Vs by 2, because the battery is rated at Vs by 2. This same voltage I shall be receiving at the load if T1 is triggered here. As long as T1 is on, I shall be receiving a voltage equal to Vs by 2 at the load. Now this is the point where the thyristor T1 is made off. Now, because it is forward biased, these two devices T1 and T2 both are always forward biased, because you can see the upper side of this battery is positive. So this circuit, this keeps these two thyristors as forward biased always. So whenever these devices are to be triggered, they are simply given a pulse here at the gate. But while commutating, we have to use the forced commutation in this. As you must have noticed here in my very first slide, forced commutated inverters. This bridge inverter is stopped forcefully at this point. So this T1 works from 0 to T by 2. This is the duration where T1 is working. At this particular point, this T1 is forcefully commutated and a pulse is given to T2. When a pulse is given to T2, the current now flows in this direction. Earlier the current was opposite to it, but now the current is reversed, and because the current is in this direction, this side will be positive, this will be negative. So you can see earlier the voltage was negative positive, but now the voltage is reversed. So we shall be getting at the output side, we shall be receiving a negative voltage which is equal to the value of this battery. Now this battery is Vs by 2. So during this half, we shall be receiving the negative supply. Now this is the point where T2 is turned off. This is the point where T2 is forcefully turned off. Again a pulse is given to T1. So if we alternatively give pulse to T1 and T2, we will get the alteration in output voltage, which is shown here. So by this technique, we shall be getting a rectangular wave at the output side. Now this is achieved for a half bridge inverter. This is achieved with the help of two devices. Now similar kind of waveforms can be achieved through a full bridge. In a full bridge inverter, this is the configuration. What is the difference? Here in this full bridge, we are using four control devices, TR1 to TR4. And if in place of transistors we are using thyristors, then it would be T1, T2, T3 and T4. And as I said earlier, generally for very low power applications we use MOSFET, and for low and medium we use IGBT. For high voltage applications we use thyristors. So this is the one which is based on thyristors. Now 4 thyristors are used here and the battery is 1. In half bridge we use 2 batteries and 2 switches. Here the number of switches are increased but the battery is reduced to 1. Let us try to understand the operation of this inverter with the help of full bridge made by the SCRs. Now if we trigger simultaneously T1 and T2 at this instant, at 0 instant, if we trigger T1 and T2, then what will be the direction of current? The current shall flow in this direction. The voltage will be positive here and negative here. This, if we consider this as the positive voltage, that means at the load side, as long as these 2 thyristors T1 and T2 are on, as long as these 2 thyristors are on, we shall be receiving the voltage Vs at the load, because it is just connected to the load, directly connected to the load. Now this voltage Vs, if it is 12 volts, the load voltage here will be 12 volts. Now at this point, we will forcefully commutate T1 and T2. This is the point where these two are commutated forcefully, and at the same time a pulse is given to T3 and T4. So this is the point, I repeat, where T1 and T2 are forcefully stopped and a pulse is given to T3 and T4. When a pulse is given to T3 and T4, what happens? The supply gets connected to load via this circuit. You can see the direction of current and this voltage is reversed. So that is why we are getting a negative voltage, because we are getting the supply from the same battery. So earlier the voltage was Vs, but now we shall be receiving a negative voltage minus Vs at the load side. Now again, this is the point where we will forcefully stop T3 and T4 and we will trigger T1 and T2. So alternatively, firing T1, T2 and T3, T4, we can get this voltage. Again, the output voltage that we are receiving is a rectangular wave, but yes, this gives you an idea about how to convert DC into AC. This from point 0 to T, this is called 1 cycle. For 1 cycle, the time is taken as T. This T is equal to 1 by F, where F is the frequency. For whatever frequency the output is needed, the devices are accordingly switched. These devices are fired for particular frequency. By just changing the firing speed, the frequency may be changed at the output side. This alteration, how fast you take this alteration, will decide the frequency at the output side. Now, one important point, you are triggering T1 and T2 simultaneously. Then you are first commutating T1 and T2 and then you trigger T3 and T4. If by chance the two devices from the same leg operates at the same time, it will create a short circuit, which is to be avoided in every case. So this is a precaution that one should take. Well, let's let's recall what we learnt in half bridge and full bridge. A half bridge inverter requires 3-wire DC supply. This may be taken as its disadvantage. It uses a three wire DC supply. It also uses 2 batteries. However, a full bridge, the number of thyristors and diodes is double, but it uses a 2-wired supply. It uses only 1 battery. In full inverter, the amplitude of output voltage is doubled and output power is 4 times compared to the half bridge inverter. So if you are using the double of the devices in full inverter, that is not a disadvantage, because you are getting the output voltage as doubled and the output power as the 4 times. Now, what is the use of this diode? For full bridge, we use 4 diodes. For half bridge, we use 2 diodes. These diodes are connected in anti-parallel to the control devices. Like for T1, the direction of D1 is opposite to it. Similar way, D4 will be connected anti-parallel to T4. Now, the purpose of this diode, it should be known. These diodes are used whenever the load is non-resistive. If the load is resistive, then these diodes are not required. For our load, only having 2 devices and half inverter and 4 devices and full inverter is enough. But for other types of load, which may have RL load, RLC load, for all those loads, we need to have these diodes in anti-parallel, because the energy that is stored in the load inductance, that energy is to be released, and these diodes will provide the feedback path for the release of that energy. So that is why I have written here that current I naught will not be in phase with voltage, and diodes which are connected in anti-parallel with these thyristors will allow the current to flow when the main thyristors are turned off, because main thyristors will be forcefully turned off. And if the main thyristors are turned off and the energy stored in the load, that energy is to be released. To provide a feedback path to those to that energy, these diodes are used. That is why these diodes are called as the feedback diodes. Now, load voltage waveform. If you look at this waveform, this waveform will never depend upon the load. Whatever is the load voltage will always be rectangular. Now, this output voltage is not dependent upon the load. Hence, we can say that the load voltage for half bridge inverter is Vs by 2 for half of the time and minus Vs by 2 for another half of the cycle. So in one cycle, because it is a rectangular cycle, it is like this voltage will be Vs by 2 and this voltage will be minus Vs by 2. This is time 0, this is T by 2 and this is T. So here in half bridge, the voltage will be Vs by 2 for this duration, while for a full bridge, this voltage will be double of this, that is V0 will be Vs from 0 to T by 2 and this voltage will be minus Vs from T by 2 to T. The load current. Now, voltage is not dependent upon load. However, the load current is dependent upon the nature of the load. And generally, the load is an RLC load. And generally, we have this load. So, I have made a small calculation based on the RLC load. If we apply the KVL in this, and for half bridge, output V0 will be considered as Vs by 2, and for full bridge it will be considered as Vs. So if we apply KVL for half bridge, we'll get this relation, and for full bridge we'll get this relation. Similar way, this is the voltage from 0 to T by 2. Similar way, if we wish to find out the voltage from T by 2 to T, then again applying the KVL, we will get these two relations. These two relations are similar to these two relations. The only difference is that here the voltage is positive, here the voltage is negative. Here the initial condition of the capacitor is Vc1, here the initial condition of the capacitor is Vc2. So in these equations, Vc1 is the initial voltage across the capacitor at time t equals to 0. Similar way, Vc2 is the initial voltage across the capacitor at t dash equals to 0. T dash here is t by 2. Now, if we differentiate these equations, we get these two equations, and by solving these two equations, we can get the value of the current. So these equations can be further solved to get the equations for the currents. Now, components which are connected in the load, they will only decide, the load will only decide the nature of the load current waveform. So let us see how the load current waveform will vary if the load is varied. So there can be these four types of load. One could be a purely resistive load, another could be an RL load, third could be RLC overdamped load, and fourth could be RLC underdamped load. So let us see how the output current varies by these four types of loads. Let's first consider the R load. For all my further discussions, I will use the full bridge circuit because full bridge circuit is the only one which is used. Half bridge was discussed just for your understanding. It is the full bridge circuit which is mostly, and in fact which is used. Now here in R load, if this is the voltage, the current will follow the same waveform because the load is resistive. In resistive load, the voltage and the current waveforms are same. For resistive load, current I0 and voltage waveform are identical and we do not require the diodes. However, the load is generally not RL, generally not R. Let us see how the output current becomes if the load is RL or RLC overdamped. Now for this voltage, since I said the load, if it changes, the voltage waveform shall remain same. So for the same voltage waveform, if the load is RL, the current will be delayed by this angle, and the time for which the current is delayed, during this time the diodes D1 and D2 will conduct. Now if the load is RLC overdamped, in RLC overdamped loads, the inductive reactance is more than the capacitive reactance, so the current is lagging here in this case as well. Now how the four devices and the four diodes will conduct, to understand this, let us take any of these two waveforms. Let me take the waveform of RLC overdamped load. If I take this similar waveform, so just uh, so that we need not to go back, let me draw the voltage waveform. This is the voltage waveform. Now in this voltage waveform, during this time the voltage is positive. However, from this point till this point, the voltage is the current is negative. Why this current is negative? Because prior to this, if I draw this voltage behind this, uh, let me draw it. This voltage was negative here, and the current and the current was earlier. Earlier, this current was flowing through T1 and T3 and T4. From behind zero, the current was taken. The current here was delivered by T3 and T4. Now, sorry, I think there is some problem. Let me redraw it. Uh, this is the current waveform. Earlier, this was take through T3 and T4. During this time, the voltage was negative. The voltage here becomes positive, and this is what the voltage is. Now, when the at 0 point, when the thyristors T1 and T2 are fired, this is the point when the thyristors T1 and T2 are to be fired, but at the same time T3 and T4 are to be commutated here. Now this is the point where T3 and T4 are forcefully commutated. So if T3 and T4 are forcefully commutated here, and the current is already flowing through them. This current is flowing through the load. Now this current cannot immediately become zero because of the inductance in the load. Now if this current is not zero, the firing which is given to T1 and T2 will not turn these two thyristors on. To turn on these two thyristors, this current should first become zero. And to make this current as and to provide the path for this negative current, diode D1 and D2 comes into conduction. So prior to this, T3 and T4 were conducting. At this point, T3 and T4 are forcefully commutated. Then the current through D1 and D2 is taken up. This is the point where the current through load becomes zero. And this is the point because here in inverter, in this kind of case, we go uh, for uh, for the continuous gate firing. So this is the point where T1 and T2 will automatically get fired because already a gate signal is applied from this point to this point. Now this, in between this, the gate is made positive. Now the gate is made positive this. So here when the current becomes zero, the T1 and T2, they comes into conduction. So when T1 and T2 starts conducting, at this point, so from this point to this point, T3, T1 and T2 will conduct, and at this point again T1 and T2 are forcefully commutated, but the load current is not zero here. So this current is to be first reduced to zero. To provide the path to this current, diode D3 and D4 comes into action, and then again here the current becomes zero. Then again T3, T4 comes in. So this is how the conduction takes place if the load is RLC overtapped. Now here the point to be noticed is the forced commutation is used, because unless this forced commutation is used, you cannot get the conversion from DC to AC in this particular case. Now let us see what happens if the load is underdamped. If the load is underdamped means the value of the capacitive reactance is more compared to the inductive reactance. Now here the current would be leading. If the current is leading, so during this time, because we have fired thyristors T1 and T2 here. So if thyristor T1 and T2 are fired here, the current will start appearing from here, and this is the time when the current becomes zero. If the current becomes zero and T3 and T4 are not fired, the current has to flow through the load, and this current will flow through D1 and D2. Now, because here the capacitive reactance is more, the effect of capacitance is more, this is the energy which is to be released through the capacitor. Now here the capacitor is releasing the energy. So during this time, the energy stored in capacitance will be released through D1 and D2. And now this is the point where the pulse is given to T3 and T4. When a pulse is given to T3 and T4, the voltage will immediately reverse and the current will now be transferred to T3 and T4. Now again at this point, the current through T3 and T4 will become zero. So T3 and T4 will stop conducting here. From this point to this point, diodes D3 and D4 will conduct. Then again T1 and T2 will conduct. T1 and T2 will again stop conducting here. So in this case, you can see that the thyristors T1, T2 or T3 and T4, these thyristors are not forcefully commutated. They automatically get commutated. Why? Because the current here automatically becomes zero. And when the current becomes zero in T1 and T2, they get commutated. Hence, we say that this is the load at which the load commutation happens. So it is not the force commutation which is happening, it is the load commutation happening. Now these equations, these tells about the turn of time, because here T1 and T2, the current through T1 and T2 becomes zero. So this is the time which it gets to turn off. So basically, if the duration of this reverse bias is more than the SCR turn off time TQ, which is the duration of this reverse bias? This reverse bias. So if this reverse bias is more than the thyristor turn of time, then the thyristors will get commutated naturally, because during this time a negative voltage is applied to T1 and T2. So automatically now this time should be suffice to get the load commutation. This method of commutation is called as load commutation, and this is in fact used in high frequency inverters used for induction heating. Now this gives you an understanding of RLC under damped load. Well, I think this is enough for today. In next lecture, I shall be discussing the three-phase inverters. These topics I have taken from the Power Electronics by P.S. Bhimra. The complete details are given in that book. However, the main points I have already mentioned in all my slides. Thank you.